Okay, talked about probability, like flipping a coin, measuring what the likelihood of getting a certain result is. Okay, we went through a lot of different types of terms. We talked about random variables, and we had two types of them, the discrete and the continuous. Who remembers the difference between discrete and continuous random variables? What did discrete describe? Whole numbers, right? So things that can be described with 1, 2, 3, 4, or 5. For example, you can't have a decimal amount of pets, for example. That would be discrete. Continuous can be described using decimals. Okay. We talked about a sample space, which is just everything that can happen, like rolling a die, 1, 2, 3, 4, 5, or 6. We also introduced the idea of a probability distribution when we deal with whole number type data or discrete data. And we said that they had to follow these certain properties, and it couldn't break one of the rules, right? And then we went around, okay, how do we actually construct a probability distribution? And we went through a few examples of doing that as well. Now we're going to start working with these probability distributions and combining all the different probabilities to find the probability of certain events, okay? And the way we're going to do that is by using these things called probability rules, okay? Before we talk about these rules, there's 3 rules that we're going to go through. I want to talk about this idea of mutually exclusive. So when we say that, when we look at events and we have multiple events, and we say that 2 events are mutually exclusive, it means that they can't happen at the same time. And what I mean by this, and I think it's easiest to describe this using examples, is, let me do one. A number being even and being odd, right? Those 2 can't be happen at the same time, right? So a number being even and being odd. They can't, there's no overlap between those 2 events, okay? Another example is turning right and turning left, right? Those 2 things can't happen at the same time. Okay, so turning right and turning left. Okay. I like a lot of examples. So maybe another one is maybe winning a game and losing a game, right? You can't do those at the same time. Winning and losing. Okay, so whenever we're using the term mutually exclusive, we're talking about things that have no overlap between them. Okay. Now we're also going to talk about things that are not mutually exclusive, so things that can happen at the same time or at least have some sort of overlap. And examples of this would be, for example, a number being odd and a number being prime, right? Those things can happen at the same time. So a number being odd and being prime. Okay. Are all prime numbers odd? What's the example of a prime number that's even? 2, right? 2 is actually the lowest prime number, and it's actually an even prime. Let me just do one more. How about a person running and a person sweating, right? So a person running and a person sweating. Okay, so mutually exclusive versus not mutually exclusive. Is everyone pretty good with the idea of mutually exclusive or not? Okay. Now this idea becomes really important when we're talking about the probability of multiple things at once. Okay, so maybe the probability of A or B happening. Okay. Now, this kind of comes into play because the idea of finding probability is different depending on these 2 situations. Okay. So first of all, if 2 events are not mutually exclusive, like running and sweating, being odd, being prime, meaning that they can happen at the same time, the probability of, let's say at one event A and the probability of another event B will be the addition of those 2 properties. So you add them up, and then you're also going to subtract their overlap. Okay. And this is because when you add these 2 together, you're adding up their overlap. So you need to take one away. Okay. So we're going to subtract off the probability of both of them happening. Okay, it makes a little bit more sense when we deal with actual numbers, so let's keep going. Okay, let's say we want to find the probability of A and B, or A or B happening, but they are mutually exclusive, so they can't happen at the same time. In this case, there's nothing to subtract off, so we're just going to add the two probabilities. The last one looks a little bit different. Okay, and this probability rule is kind of like the opposite rule. It's also called the complement rule, and I'm going to write that down. Complement rule. Okay, and let's just kind of read this. Okay, if an event AC is the event that A does not occur. Okay, so AC we call A complement. And all that means is it's kind of like the opposite of A. So if A was riding a bike, AC would be not riding a bike. Okay, so it's just the opposite of something occurring. Okay. When we want to find the probability of the opposite of something, we're just going to take one and subtract it from the probability of its opposite. Okay. Now I know this sounds really abstract. Let's do a few examples and maybe you'll clear things up. Okay. So we have example number 9. We have a card and it's being drawn from a stack of cards and they're all labeled 1 through 9. Okay, so just a stack of cards, label 1 through 9, picking a card from the stack. Okay, what do you think the probability of picking a 1 out of the stack is? 1 out of 9, perfect. And picking a 2 is? I heard 2 over 9. It's actually going to be 1 out of 9, right? Because all the cards have a yeah, I think I was trying to trick you there because it does seem like it should be 2 out of 9, but since all the all of the cards have an equal chance of being chosen, actually all these probabilities are going to be 1 over 9, right? All right. Yes. Now, if you want to, you can check to see if this probability distribution follows the 2 rules of a probability distribution, and they do. Okay. But let's think about this. Okay, the first question is we're trying to ask if these events, like picking a 1, picking a 2, picking a 3, picking a 4, and so on, are mutually exclusive. So this question is asking us, can I pick a 1 and a 2 and a 3 and a 4 at the same time? Is that true? Who thinks they're mutually exclusive? Who thinks not mutually exclusive? Okay, why do you think not mutually exclusive? Anyone want to explain? Megan?
Is it maybe because one card at a time, so starting 2 and 3?
Okay, yeah, so you're picking 1 at a time. So can you simultaneously pick like a 2 and a 3 at the same time? If you're just picking 1 card? Good. So would you call this mutually exclusive or not mutually exclusive? Mutually exclusive. There we go. We were on the same idea. It's just learning how to use this word, right? So things that can't happen at the same time are mutually exclusive. Does that make sense? Okay. So this is mutually exclusive. Okay, and this is because they can't happen at the same time. You can't pick a 2 and a 3 if you're just picking 1 card, right? So can't happen at one time. Okay. So here we have an example. We want to find the probability that X, or the card that we pick, is a 3 or a 4. Okay. Looking at our mutually exclusive rule, how can I rewrite this in terms of our equation? First of all, what rule am I using? The first one, second one, or third one? Second one, good. And how can I rewrite the second equation to look like this example? How can I separate this into 2 probabilities? Yeah, p that x is 3 plus p that x is 4, right? Because in this example, A was technically that x was 3, right? And B was the second one, that x equals 4. So putting them in the formula gives us that this is x equals 3 plus x equals 4. Does that kind of make sense?
You're supposed to solve that.
It's actually a little bit easier with solving. I know it looks really strange. Let's see how we can make this a little bit simpler before we think about solving. Okay. What is p x equals 3? Looking at your chart. 1/9, right? Because looking at my chart, let me look. P x equals 3 is that, right? Okay. P the x equals 4, looking at my chart, same thing, right? So it's just 1/9 plus 1/9. Answer is 2/9. Any questions on part B? Okay. Let's talk about part C. Part C is going to generalize this rule that we just used, okay? Now, we want to find that the probability that x is an odd number, okay? And before I even go ahead and work with this, I think I can make this a little bit simpler than saying odd, okay? Taking a look up here, the odd numbers are 1, 3, 5, 7, and 9, right? So the probability of an odd number is the same as saying the probability that x is 1, or 3, or 5, or 7, or 9, right? Okay, so this is the same thing as saying odd number. Okay. Now I know there's no rule that says the probability of one thing or another, or another, or another, or another, but do you kind of see a way to generalize this using what we did in part B? Yeah, right, because isn't this the same as using this rule multiple different times? So this is the probability that x is 1, plus the probability that x equals 3, plus the probability that x equals 5, plus the probability that x equals 7, plus the probability that x equals 9. Okay, because we have these mutually exclusive events, we can just generalize that rule from the last page into a bunch of additions. Okay, so that's 1/9 plus 1/9 plus 1/9 plus 1/9 plus 1/9, and I think that gives us 5 9s. Okay. Any questions so far? All right. Let's get a little bit more theoretical here. Okay, let's say that we wanted to find the probability that x was 3 or odd. Okay. Are the events x equals 3 and x is odd, are those two mutually exclusive? Can they happen at the same time? Who says mutually exclusive? Who says not mutually exclusive? Okay, who wants to explain? Alan? Yeah, right, 3 is an odd number. So if I picked 3, it would both be 3 and an odd number, right? So this is actually not mutually exclusive. Okay, because there is a way to get 3 and an odd number at the same time, okay? So we can pick 3 and an odd number at the same time. We can do that by picking 3. So let's do part E. We want to find the probability that x is 3 or x is odd, okay? We're using formula 1 now. Can someone explain how we can write this out in terms of the formula? So it'd be p of something plus p of something minus p of something. Mm-hmm. You got there. You're almost there. Any guesses? Okay, so this is the first thing. So A would be that x equals 3, right? In our formula, we have B, which is the second thing, which says that x is odd. Okay.
But it has to
Yeah.
be 3 though. they're the same.
Mhm. But using the formula, I'm just gonna fill in the blanks and then we can think about the probabilities. So the formula says P of A plus P of B minus P of A and B, right? Okay, so I guess B is X is odd. So I can just stick that in my formula, right? Then A and B is just putting them together with the and in the middle. So this is X equals 3 and X is odd. Oh my God, I can't spell. Okay. Do we all agree that the formula gives us this? Okay, good. Okay. Now, this gets a little tricky. The first two are easy because we already found them. What's the probability that X equals 3? 1/9, good. You might want to take a peek at the last question. What's the probability that X is odd? 5/9, right? That was from part C, okay? The last one is a little hard, okay? We want to find the probability that X is 3 and X is odd. What is that essentially asking us to find the probability of?
Adding them together.
Not just adding them together, Ashley. Not quite. Isn't it just 3, right? Isn't the probability that X is 3 and
And,
yeah, isn't 3 an odd number? So the only way we can get 3 and an odd number is if we just get 3, right? So another way to say this is the probability that X equals 3. Okay, so I know it looks weird, but X is 3 and X is odd is basically a redundant statement. It's basically saying the same thing kind of twice. We know 3 is odd, so this is just the probability that X equals 3. Okay, piecing this together, we have 1/9 plus 5/9 minus 1/9. Good. So that gives us 5/9. Okay. Any questions on part B? Okay, this one was a little bit tricky. You kind of have to realize that, okay, putting them together means that we have just X equals 3 and we're good. Okay. Let's do one last one. I'll let you on your own. Okay. We want to find the probability that X is not 5. Okay. Thinking about this, picking 5 versus picking any other number, is that mutually exclusive or not mutually exclusive? Actually, we don't even have to think about mutually exclusive or not here. Let me actually show you 2 ways to do this. Okay. What rule do you think we should be applying here? The complement rule, because it says not 5, right? Okay. So I want to use rule 3. Okay. I know that AC notation is kind of weird. This says not 5. So technically, that's got to be AC, so it's not, okay? So using my rule, what do you think I can, how do you think I can write this rule in terms of the question? The 1 minus the probability of what? Well, what's the opposite of X not being 5? X being 5, right? So the probability that X equals 5 is the opposite of X not being 5. Okay, now that I wrote this out, probability that X is 5 is 1/9, right? We have fractional subtraction here, which is kind of crazy, but I think we can be able to do this. When we subtract fractions, we need to find a common denominator. Looks like that's going to be 9, right? How do I write 1 as a fraction over 9? 9/9. And it looks like I'm left with 8/9. Any questions on how I use the complement rule here? Now, there actually is a way to use a different rule here. And let me show you how to do this, okay? We can, so this is an alternate method. We can rewrite X is not 5, right? Another way of saying that X isn't 5, well, there's all these numbers that aren't 5. We've got 1, 2, 3, 4. Well, 5 can't be in there because we're not finding 5. 6, 7, 8, 9. Right? So this is the same thing as saying not 5, since there's only 9 things, we can write them out. Then we'd have to do the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. And I'm not going to write this all down. I'm going to put these dots plus the probability that x equals 9. And, well, you'd be adding 1 9 to itself 8 times, right? And it would give you 8/9. Okay, so you can do this, but this takes a lot of work and a lot of writing. And I think it is easier to use the complement rule in this case than just using the first 2 digits. Any questions on part F? Okay, I know I threw a lot at you. If you flip the page, we have another example. I'm going to go through the probability distribution with you just to make sure that we all have the same probabilities, and then I'll let you go with the questions. Okay. So we have a basket. We have 3 green grapes, 3 yellow peaches, and 4 green pears, and we want to select a piece of fruit, right? What do you think the X values are going to be? Yeah. Green grapes, yellow peaches, and green pears. Okay, how many total pieces of fruit do we have? Right? What do you think the probability of a green grape is? 3 out of 10. Yellow peaches? 3 out of 10. And what about green pears? I'm going to keep it as 4/10 just because it might make things easier, but you can write 2 things too. All right, I'm going to give you a few minutes to work on A through F. You can work together if you would like to, and I'll come back in a little bit. All right, so let's come to the front. As I've been walking around, it seems like all of us seem to be on the same page here. So we came up with a probability distribution, so we're doing pretty good here. Our first question asked, okay, the individual events like getting a grape or getting a peach or getting a pear, are these mutually exclusive themselves? And I forgot who I asked to write this one up. What's this, Alex?
So yeah, those,
Yeah, so why did you say yes to mutually exclusive?
because you can't, like, if you're just picking one at a time, you can't get like a grape, a peach, or a pear at the same time.
Yeah, right. You can't pick up a grape peach or a peach pear, right? Nice job there. And then I got Alex to write up, okay, how do I find the probability that X is a peach or a pear? And how did you get this probability?
So I just added the probability of getting a peach, and then I added the probability of getting a pear to get some.
Nice job. Any questions on A or B? All right, moving on to part C. This one was asking us to find the probability that something was green when we picked it up. Who wrote this one? Emily. There we go. Emily, do you want to kind of explain how you got this answer? Perfect job. Any questions on part C? All right, moving on to part D. Now I wanted to find the probability of maybe getting a green fruit or getting a grape. And this one was asking us, are these 2 events mutually exclusive? Forget who wrote this one. Was that Maya? Do you want to explain why you said not mutually exclusive here? Yeah, right. You can get something green and something that's a grape at the same time by picking up a green grape, right? Okay, so can you take us through how you found the probability of finding something green or something that's a grape? Mhm. Mhm. Perfect job. Any questions on part D or E? Moving on to part F, this one was asking us to find the probability that something wasn't a pair, which is a little bit different than what we've been doing so far. Kelly, do you want to explain how you got this one? Mhm. Perfect job. Any questions on parts A through F?
So for F,
Mhm.
I thought you were trying to find everything but a pair. So you put in add 3 plus 3.
Oh, okay. So I think I think I see what you're saying. So you're like, okay, I'm gonna find the probability that everything is a pair. So isn't that like the probability that something's a grape or a peach, right? Okay, so you found everything that wasn't one. Let's see if we can do this the same way. Okay. Now, getting a grape and getting a peach are mutually exclusive, which means they can't happen at the same time. So I guess you can kind of split this up into the probability that X is a grape plus the probability that X is a peach, right? Okay. What's the probability that X is a grape? 3/10. And what's the probability that X is a peach? 3/10. And when we add them together, looks like we got the same answer, right? So this question actually has 2 different solutions, and I'm actually kind of proud that some of you did a different solution than others. So we have 2 different types of solutions going on here, but both are totally fine.
I'm so sorry, but I thought then you're supposed to do 1 minus that 6.
Yeah, that's what I thought too.
Oh, okay. Okay, I think I see where the confusion is coming from. So this is using rule
Oh, that's all it's
2, right? Yeah, and then this is using rule 3. They're 2 separate rules that aren't like connected at all. So if you decide to use rule 2, you're not going to do 1 minus because rule 2 only tells us to add. Rule 3 doesn't tell us to add anything together, it just tells us to do 1 minus. So rule 3 is a little bit different than rule 2. I hope that makes sense. All right. Good question though. Any other questions on A through F? Oh, it doesn't matter. No, it doesn't. I would say rule 3 might be a little faster if the question's really big. So like if there was a big chart with like 100 probabilities, maybe you wouldn't want to add them all up. But I probably won't do that to you. So yeah, it doesn't matter which one you use. All right. Any other questions? Good questions here. All right. How about this? What time is it? Okay, I do want to explain one more thing and then I'll let you go. Just to kind of put this in your mind before Wednesday, okay? There's these things called probability histograms, okay? And when we have a probability distribution, it looks like this. I know it looks a little bit different here because it's turned on its side. Like you're used to seeing the probabilities on the bottom and the X values on top. But these are all our X values, and to the right, we have each of their probabilities, okay? Because we have this, we can stick them in a histogram, right? So the probability of 0 is 0.03. So the height is its probability. The height over 1 is the probability of 1. The height over 2 is the probability of 2, and so on. Okay, so we can see probability histograms come up as well. All right. I guess I don't think we have enough time to do the next set of questions. So I'll let you out a little bit early. Okay. And I guess we'll talk about this on Wednesday.